Hello, this is a very upset dead hamster who has just finished recording an hour-and-a-half video only to find that OBS wasn't registering his microphone. So we are going to go from the beginning and re-record the entire video from the start and hopefully cover as much of the topics as we did before this. I am incredibly demotivated. However, we're going to go through this anyway, so welcome. Today, we are going to be covering how Mario Kart 64 works, Part 2, Take 2. And today, we're going to be specifically discussing how FedEx commands actually draw the geometry. When I refer to FedEx commands, I am referring to F3DEX. As you may recall in my last video, F3DEX is the microcode that Mario Kart 64 uses to draw its triangles and course geometry, as well as all other 3D rendering. Instead of calling it F3DEX, I will be calling it FedEx because this is easier and simpler, and also because I just recorded this for an hour and a half, and I'm going to do whatever is easy and simple. So, continuing on. What is FedEx again? It's the microcode that is used to draw triangles. We have covered before that there are display lists. So we're going to load up a modified version of Mario Kart 64 where I have adjusted the jump height of the characters. The reason we're looking at this is because of a code, a GameShark code that exists. This GameShark code will re-enable the debug menu that was left out of the game by the developers. They had a debug menu throughout development that was utilized to test certain aspects of the game and see how it functioned. So the code was left in the game and simply disabled so that users would not be able to access it. But with a couple GameShark codes, we're able to re-enable the deactivated debug mode and to see the features that it had. Now, because I've modified the ROM, it no longer Project 64 does not recognize it as being Mario Kart 64. So we have to re-enter these cheat codes and proceed from here. So again, the modification we've made is to the jump height of the characters. We've made it so that they can jump higher, specifically Mario, so that I'll be able to demonstrate some of the display list and some of the things going on. So again, when referring to display list and section views, we're speaking about the way that Mario Kart renders its geometry. If you haven't watched the last video, you need to stop watching this one right now and go back to it. This is a series that is meant to be watched in order, and each video is building upon information presented in the last. Just a quick overview as a reminder. This is the section view for Section 1 North. When a character is driving on the polygons in Section 1 and facing north, this is the section, the polygons rather, that are actually going to be drawn to the viewer. So we'll go here. To activate debug menu with the cheat code on, we're going to hold L and tap Z. We'll turn debug mode on, and we're going to edit Mario's circuit. So you see right away there are some additional bars and options. The bottom ones are for the current processing loads for the graphics and sound and ASM commands and everything else. What we're most interested in is that text and value. That is facing north in Section 1. Now I'm facing east, and now south, and now west. And depending again on where I'm located and what view, different objects are drawn. We're going to hop up here using our edited jump height to see that when facing east, none of these objects over there are drawn. You'll see several objects are drawn. These are ones that are referenced via ASM commands that are located in segment 6. Rather, the geometry is located in segment 6. So these are always drawn. The trees are object lists, always drawn. The rest of the geometry is based on the section view. If we go here, we'll see that section 1 east is this geometry here, and it matches up pretty perfectly. We see this cliff face here, this triangle, and this triangle, representing these two triangles here and here. And if we were to slightly rotate, we could see that this area and this are not being drawn, but that this road right here is being drawn. Now we're going to take that a step further, proceeding. Here, in section 2, immediately upon moving from this area to this area of the course, if I were to rotate, you'd see that immediately upon crossing over this line, Bowser, you dog, we would be in this section view here. So from section 2 east, we're going to proceed forward just a smidge. Now comparing section 2 to section 1, you see that they're almost identical with the exception of these polygons now being drawn and some of the back ones here not being drawn. So we're going to see if we can see this object right here by hopping. And as you can see, this area here is now being drawn in, whereas in the last section view, it was not. So this is all recapping on the previous video. What we're actually going to be looking at in this video is how FedEx commands work and what they're actually doing. So when we're calling a display list, that's just calling a list of commands located at a specific segmented address in the game's files. So we're going to take a look at that now by going to Mario's Raceway's master display list and looking at the commands that draw this first section view here for section 1 north. So we'll close Project 64 and begin taking a look at Mario's Raceway segment 9. And right here is where we begin the master display list. This first address here, it's segment 6, offset 0. We have the beginning of the display lists that will draw section 1 north. So when we go to segment 6 and go to offset 0, we'll see a command BC. This 8 bytes here is the first FedEx command. All FedEx commands are 8 bytes long, or 32-bit instructions. The first byte is the opcode, in this case BC, followed by 7 bytes of parameters that are dependent on the opcode. For the most part, BC is setting up an RSP address. Micro has all of these mapped out. Now, not all of the FedEx commands are mapped out, but many of them are. And you can see here that this is setting segment pointers in the RSP for data that's getting loaded. I don't know the specifics. As you can see, even Micro might not know the specifics. We don't actually have to. For a lot of Mario Kart, there are only specific parameters that are available. For example, for FedEx commands, the course geometry is saved in what's called segment 7, and it's a truncated version of FedEx. It only allows 6 texture types. You can only load vertices and draw triangles, and then it compresses this in a special bytecode that is much smaller than traditional MIO0 compression. So for the majority of course compiling and FedEx commands related to that, these things are standard. They're set with specific parameters, and then you draw your triangles from there. So for these parameters, we mostly will not be touching them. This is actually one of the first commands that we will be looking at. It's an F5. When we look at the opcode F5, that is setting tile, the texture parameters. The first one, the opcode F5, followed by an 8-bit unsigned integer that is split into to bits. So the first 4 bits of this 8-bit unsigned integer is going to be the format of the first 3 bits. No, the first 4 is going to be the format of this texture. So looking here, you can see that it is format 1 followed by a size in line of 2, or 0 rather. Again, most of these are going to be pretty set because there's only 6 options that you have. You can have either 32 by 32, 32 by 64, or 64 by 32 textures. Those are the dimensions. And your options for compression are either using RGBA 16 or CI 8. So what Overcart does is it figures out which of those 6 texture parameters you're trying to write, and it just writes out the opcodes with the parameters for that specific texture type without actually calculating any of these parameters. Now in segment 6, you aren't limited as you are in segment 7, and you could write out full FedEx instructions. This is how the dynamic objects, such as the eggshell in Yoshi's Valley or the spinning signs in Mario's Raceway, are written. Those are written into segment 6, and again, you have access to the entirety of the FedEx instruction set when you're writing there, because it only uses basic MIO0 compression. But for the majority of what we're dealing with, we are going to be limited. So again, this command is pretty standard because it's one of 6 options for our intents and purposes. Next opcode, F2, is setting the actual size. This again is almost always going to be the exact same setup. If it's a 32 by 32, these first values are always going to be 0 because it's always going to be the bottom or the top left corner of the texture, 0, 0. And then the bottom right value is going to be based on the texture size. S and T coordinates, as opposed to U and V, are not based on 0 to 1. Instead, they're based on 0 to texture size. So if the texture is 64 pixels wide, then this would be representing 64 pixels across for the S and T coordinates. A little bit different than how U and V coordinates are done, a little bit outdated, but that's what we're dealing with Mario Kart 64. So moving into the next command, FD. FD bytecode sets the texture location to actually load the pixel data from. So again, the first 3 bytes here, the first 3 bits are the format that we're loading. In this case, it's an RGBA formatted texture. If it was a 2, we would be doing a CI8, but it is a 0. The following 2 bits are the size. This is doubled, so in this case, these 2 bits, 10 is 16, so it's 32 that we're loading there. And the width, always 0. That would be these final 4 here. Once that's loaded, or once those parameters are set, it then gives you the actual segmented address. In segment 5 at offset E000, we have the actual texture data. The textures are written end to end. They are loaded out of the ROM and decompressed and then written to segment 5. So at offset E000 is the beginning of the pixel data. It goes on however many bytes the sizes, and then it finishes loading, and the next texture begins immediately after that. For example, if you wanted to see how that looked, here's segment 5 for DK Parkway. As you can see, one texture ends immediately in the ROM, the next texture begins getting written. They are written end to end, they are not individual files. After that, an E8 again is going to be an RDP sync. When you load data into a parameter from the RSP, you have to do an RDP sync. I don't know what it does, but that's what they do, so we do it too. And then for some reason they seem to set a texture parameter again to some weird settings. I don't know what it does. It doesn't really matter. We just do the same thing, and it works. So a lot of times we don't really know what these, or at least I don't really know what these commands are doing, but I know that they seem to be the exact same for every display list. So it seems to be setting some basic parameters up in order to draw triangles, which is what we're really looking after. So after setting all these parameters, it actually gets into the first display list call. So again, we are drawing section 1 north. So 06 is the opcode for loading a display list, call list. So the next 3 bytes are unused. And then you have an RSP address, or a segmented address. What this is saying is that in segment 7, at offset 1770, we have the instructions to draw this object that we need to draw. If we look here, 1770 is this object right here, the second area of road. I'm actually going to grab a bottle of water. I'm quite parched after all this talking from the first video that failed and now this one. So give me just a moment and I will be right back. Okay, so continuing where I was. Again, we're now drawing this object that is located at offset 1770 into segment 7. So if I were to go to segment 7 and proceed to offset 1770, you would see these commands here. BB is the start of a display list. There's an alternative I can't find it now. There's an alternative command that also starts a display list. It starts it upside down. I don't know the exact, actually it might just be this here. Whatever it is, it's used, I believe, to draw triangles on the back facing of objects, so that you could draw a two-sided triangle without having to use another face for the other side and actually store the vertices and the indexes for a second face using the back facing. I don't know specifics. It's, again, not too important for the majority of what we're dealing with Overcart. After the BB command, it immediately goes to loading vertices using command op4. When we look at opcode 4, we see that it's loading a vertex into the vertex cache. Now, the way this works, the first opcode is not 3, it's 4. The index is the next 7 bits. The final bit of the unsigned 8-bit integer isn't used. So when we look here, we can see that all 8 bits are actually 0. What that means, now with the vert cache for FedEx, we can load up to 32 verts at a time. We're able to load 32 verts. We can draw triangles with those verts, and then we have to load more verts if we need to. We cannot load more than that with modern systems with a large amount of memory. The entire model is usually loaded at once. The entire vert cache is loaded at once, and you can reference any index in the entire vert cache to draw triangles. These older systems did not have a lot of available memory, and so they had to make do with what they had, and they could only load 32 verts at a time. So the index to load to in this case is 0. So we want to start loading at index 0. What you could do is load 10 verts. As you can see, the next value is the number of verts to load. So you could split and load 10 verts from index 0, and then go to index 100 and load 10 verts, and then go to index 217 and load 12 verts and get your 32 verts that way. The game won't do that. It's actually pretty difficult to be able to set up your vertices that way. You would have to know where all these objects are, and it's a very convoluted setup that really wouldn't be efficient unless you had an enormous amount of planning going into each individual course. For that reason, what you'll see most often is loading 32 verts at index 0. So completely replacing the entire vert index with an entire new set of verts, and then drawing triangles based on that new set of verts. So after the number of vertices to load, which we're going to look at right here, the first 6 bits, 1, 2, 3, 4, 5, 6, and if we were to see what that value came up to, so we have 1, 2, and then the 6 bits, we'd be loading 32 verts, just like we had mentioned. So back again, at index 0, load 32 verts. The number of bytes is the final 10 bits. When you're dealing with the vert cache, when it's loaded into memory, the number of bytes that a vert takes is 16. It's a 16-byte chunk of data. When it's stored in file, it's only 14 bytes. They actually, what the game does is when it loads the verts into memory, to make it simple to progress through, they use a 16-byte structure as opposed to 14 bytes. That way, when there's 2 verts back to back, it takes 32 bytes. Everyone loves powers of 2. They're nice and clean. That also means that the size of the memory address that's holding all of the vertices will also most likely be a power of 2, or will be a power of 2, because it's using a 16-byte structure. So what it does to do that is it just adds 2 unsigned integers. It doesn't appear to have any value or any use. Again, I believe it's just padding to round out and buffer out the size of the vert struct. What that means is that if we have extracted this data here from the ROM, we can't use these offsets directly. We have to do a little bit of converting. So this offset is pointing to the memory address of in segment 4. So if we look here, in segment 4 at offset 4250, we're going to load our vertices. However, we're going to have to do a little bit of math. So we're going to do it all in decimal here so it's easy to read. 16,976. That's the decimal offset that we would be loading our vertices from if it was in memory. Now each vertex is 16 bytes. So if we wanted to figure out what vertex we're loading, what vert we're loading, we would have to figure out, divide it by 16, which is the length of each structure. So if we're going 16,976 bytes in, and we want to figure out how many verts that is, we have to divide by the size of each struct, which is 16. That's going to give us the 1061st vert in the file. Now, if we want to find out where that vert is located in our extracted file, we're going to multiply it by the size of the vert struct that is in the file. So again, to figure out what vertex it was, we divided by the size of the struct in memory. And now to figure out where it is in the actual extracted data, we're going to multiply it by the size of the structure there. So we take the index, multiply it by 14, and at this offset, I will have the data for the vertices that we need to load. And remember, we're going to be loading 32 of them. We're not actually going to do anything. What we're going to do is go to this offset in decimal and compare the values we see here with the triangles and the vertices that are drawn here. So going back to segment 7, we've just finished loading the verts into our vert cache. Remember, this is for the display list of 1770, the first display list we've called for section 1 north. We did a whole bunch of parameters to set up some textures. Specifically, I'll even show you what texture we set up before we get any further. Where were we? We were right here. We set up FD at E000. If we look at Mario's Raceway, at E000, we're loading this texture right here. 64 by 32, half of the road. So again, fast forwarding to 1770, we go over here, we've loaded our vertices, we're now going to do B1. If we look at the FedEx opcode for B1, we'll see that that's to draw two triangles. The game is almost always going to draw two triangles unless it's unable to, unless there's only one triangle left. If that's the case, it will use the opcode for drawing a single triangle. For B1, the opcode is followed by three unsigned 8-bit integers. Because of the way these values are stored using only 7 bits, you can actually take this value and divide it by 2 to get the actual vert index. It's just a quick workaround. The proper way would be to be reading the bottom 7 bytes and then to determine the value from there. But because of the way that bits and math work, you're able to just divide it by 2. So what this is saying is that using index 0, index 1, and index 2, draw a triangle. So going back to segment 4, we're going to look, this would be index 0, the first vertex that we've loaded, and this first value is the x value. Now if we were to look at what the x value is, it's saying it's negative 50. And here, with this triangle, we see a vert here with an x value of negative 50. Now there's actually two verts that have an x value of negative 50. We're going to have to see which one it is. Now the next value is listed as y. However, Mario Kart 64 is an early 3D game. With the developers of 3D games were first getting started, they were a bit unfamiliar with, well rather, they were pioneering how we now think of traditional coordinates. In 2D games, when you design a level, you have an x value, which goes from left to right horizontally, and you have a y value, which goes up and down vertically, like your line graphs back in grade school. When you're dealing with depth in a 2D game, that would be using what is called the z-index. And the z-index determines what sprites or what images are drawn on top of each other. So for example, Mario passes in front of the background, but perhaps when he passes through a goalpost, the front goalpost should be in front of him. So it looks as though he's running through it. In that case, the front goalpost would have to have a higher z-index so that it was drawn on top of Mario. When these same game developers transitioned into making 3D games, they kept those same coordinates. X was horizontal, Y was the height of an object, up and down, and Z was the depth, front to back. Now, in a modern 3D editor, that is not how it is done. X is still left and right, the horizontal. Z is used for vertical, for height. And Y is used for depth, or for how far back and forward an object goes in three-dimensional space. Now, to properly use modern 3D editors and create content for this game, we flip the YZ axis when we store this model and write it into the game files. So all the Y values become Z values, and all the Z values become Y values. Additionally, because this game treats depth backwards from the way that modern 3D editors treat depth, when we invert the Z and put it towards the Y dimension, we have to invert the value. So if the value was originally 500 Z, it would be negative 500 Y. So, looking at this, the Y value should be 0. And if we look here, I apologize, the X value is negative 50. The Y value should be 0, which it is. And the Z value should be negative 617 or negative 500. And in this case, it is negative 617. Those three coordinates point to this vertex, and this is the first vertex that is used in this display list to draw a triangle. The next one would be vertex or index 1. So going back here again to segment 4, we now have the next vertex to get to. So following the x, y, and z values, we have the s and t coordinates. followed by the R, G, B, and A values for the actual vertex colors. So going here again, we had X, Y, Z, the S and T coordinates, and then R, G, B, and A, leading us to the second vert right here. This vert is located at X negative 50, Y 0, Z negative 500. You'll recognize that as the other vertex we were looking at. So the first triangle uses this vert and this vert, followed by, and what we're going to do is we're going to go here and just move forward by 14, and that'll put us at an X of 50, Y or Z of 0, and then 500 for the Y, which is this value here. So the first triangle drawn by the display list, which is this command here, is this triangle right here. After that, it then uses indexes 0, 2, and 3. Now we remember before, indexes 0 and 2 were these two verts here and here. If we were to look at the following vert in index 4, by again going forward 14, we would get an X of 50, a Z of 0, and a Y of 612. X50, Z0, and Y of 612 would be this vert. So the first command for B1, drawing two triangles, would draw these two triangles located right here. You'll notice that the way the opcode is set up for B1, it draws a triangle, rather it lists the opcode of B1, then lists the indexes of the triangle. It then has a blank int8 spot, which is padding, to match the B1 command, and then again the three unsigned integers, which represent the triangle vert indexes. So having drawn these two triangles, the next command will again draw two more, and two more, and two more, and so on and so forth until we've gotten to loading more vertices. We'll then draw more triangles. One more, that's so unfortunate. We had to load verts just to draw last two triangles. And then the B8 is an ending of the display list. So at this point, having drawn all of these triangles, we have drawn the entirety of this object, and we can now return to the display list that called us. We would go back to segment 6. Having finished this FedEx command, we would now proceed to the next FedEx command and draw the object located at 16D8, which is this section of road right here. I'm going to take another pause to grab a drink. Thank you for your patience. So, having drawn this object, we would proceed to draw all of the remaining until again reaching a B8. Just as when we followed one of these display lists and received a B8 command, this ends the display list here. Upon finishing this display list, we would go into segment 9 where we started, and this would be the entirety of section 1 north. Now, one of the strange, obscure things this game does is it actually uses vert colors to determine out-of-bounds areas. Normally, the colors will be 252 at their highest, as opposed to 255. Certain verts, such as these out here, will have their G value of 253. These are out of bounds areas. I don't know all the reasons why the game did this, but one of the ones that jumps out is so that half a display list could be set to be out of bounds without setting the entire surface area to be out of bounds. Again, seems a little strange and an obscure way of handling it, but the vert colors are also used to denote out of bounds areas for the game. After processing a display list for that region, again, it would come back and start from the beginning, and then process the next display list until it had completed them all and gotten back to the original call that had begun them. When you're proceeding through display lists, you'll notice that most of these were separated based on material. One of the bottlenecks the system has is loading raw data from the RAM, or from the ROM rather, the cart, into memory. So when you're loading textures or vertex data, that's triangles that you're not drawing. Every time you're processing a FedEx command to load verts, you're not drawing two triangles. You can see too, loading a texture takes up a significant number of commands. You're dealing with 6 or 7 FedEx commands to load a texture into memory. So using too many of these in a display list, or going back and forth between materials, is going to have a serious impact on your performance and the way the game is rendered. One of the courses that is famous for this is DK Jungle Parkway. Many people know that DK Parkway was added very late in the game. It wasn't sure if they were going to be able to get permission, is how the story goes, to use Donkey Kong, and so without early confirmation from Rare, they had Magikoopa in as a character instead. They were swapped out and replaced with Donkey Kong, and his level was added near the end of development as well. It's one of the last courses made, alongside the battle courses at the end of development. Mario's Raceway had 17 sections rather. DK Parkway has 26. It's quite a long course, quite a lot of objects, and quite terribly made. This course is famous for its poor performance. Something interesting this game does that you have noticed but probably discounted and just chalked up to your imagination. If you were playing multiplayer mode with friends as a kid and noticed that in 4-player the game seemed to be kind of sluggish and choppy, you were correct. Something the game does in the background with multiple players, depending on the course, it actually renders additional physics frames instead of visual frames. So naturally, the game will run 2 frames of physics for every rendered frame that you actually see displayed on the screen. So every time the game displays a frame and your character moves in that frame, there's 2 physics frames that are going on in the background that are actually calculating the position, movement, speed, and all the other variables that are going into the race. However, when you have multiple players rendering a very high density course with a lot of FedEx commands, you're going to get lag, just like every N64 game. It did not have a variable frame rate that would allow the frame rate to drop and compensate and allow the game to run at a smooth performance level. Especially in games like GoldenEye, when you used explosions, you saw this. The whole game crawled to a slow still. The game still runs exactly as it's supposed to. The physics would be perfect as it's supposed to be running. The calculations would still be right. It would just be slow. So to the player, your timing, your gameplay, your performance would be affected, because you would be constantly having to adjust your racing to the course's variable frame rate going in and out, and causing impacts to performance. So what the game does instead in the background is it renders additional physics frames in between each of those rendered frames. So you can see when two-player mode for DK Parkway, the value is 3. So every time the game shows you a frame and renders it on the screen, in the background it was calculating physics 3 separate times before it rendered that frame. When you get into 3-player mode, you can see that it also does it for a couple other courses. And when you get into 4-player mode, it does it for nearly every course, even one of the battle courses. And for DK Parkway, there is a 4-time multiplier, which means there are 4 frames of physics for every 1 frame that is rendered. Now, something important is that you'll notice these are listed as input frames. Additionally, as well as being the only frame that's rendered, it is the only frame where an input is taken from the controller. So when playing on 4-player mode in DK Parkway, you're actually there's something called temporal resolution, which is how much time is in between game ticks, or how much time is in between frames. And because the game is running faster in the background, you're not able to properly input your input frames, and that's why the game feels so sloppy and loose when you're playing with 4 players on DK Parkway. It's very poorly made, very inefficient. And we're actually going to go into that now. My last video, when I discussed and went over this, I had a lot of people who seemed to be interested in the concept of why DK Parkway was poorly designed and what about it is made bad and how it could be done better. So I actually wasn't expecting in my last video to find such glaring examples of poor design, but I actually found them everywhere. Everywhere I looked, I found examples of what not to do when designing a course for Mario Kart. So we're going to take a look now at take 2 of the video and really go in depth and look at everything that this course is doing wrong. So for starters, this is section 1 North we're looking at here. And you'll notice, I'm actually going to load up Mario's Raceway first. There we go. So we're going to look here as object counts for Mario's Raceway. Looks like this is probably the largest section view right here with the most objects. This one is the entire course, so that doesn't count. This one looks like it's the most, and we're looking at a total of 653 polygons. Some of these 566, 621, so yeah, none of them in Mario's Raceway have more than 653 polys rendered at the same time. So again, this is each section view is only rendering a part of the course. At the absolute worst, we are going to render 653 polys all at the same time in Mario's Raceway. Then you go to DK Parkway. Right off the bat, section 1 North. Doesn't look like a terrible amount of geometry here. As you can see, not a lot going on, just the opening area where you would start the race, the cave behind you, and the first turn around the corner, as well as some geometry across the river that you would be able to see. This right here is 1,500 polygons to draw section 1 North. 1,500 polygons. Again, Mario's Raceway was 653, and that was the largest display list. There is a display list with 2,200 polys being drawn. This is ridiculous. It's further ridiculous because there's no need for most of this geometry to even be in the display list. This right here being missing says that the player has to be at least this far in the course, because if the player was on this object, they would be able to see this missing geometry. If they were standing right here, the camera would be positioned right about here, and this would be missing. The game doesn't do that. So again, what that says is that the player must be at least this far into the course, which would make sense. This is an east section view. This one is for north, this one is for east. So if the player was right about here, facing in this direction, this is the geometry that would be drawn. What's very interesting is that half of this doesn't need to be. I would say that all of these objects, and all of these objects, and all of these objects could be completely ignored, and the entire display list would still look the same. Because if these objects were missing, sitting here and looking east, you wouldn't even notice. They are all behind the camera. This one isn't even the right object. It doesn't even have all the vertices it needs, so it doesn't match the edge here. But again, it's behind the camera. The objects are out of sight. And you notice when I selected these, that's 775 polygons that do not need to be drawn. We can delete these entirely, and the player would never know. They would still see the exact same view. There it is. There's the difference between having them and them being deleted. There they are, and there they go. No difference at all in the view that we would have for this course. And that's 770 polygons that could have not been drawn for this section view. Again, over 2,000 polys. It could have had an entire course. Mario's Raceway's worst polygon count was lower than the amount of polygons I could have removed from this section view. Furthermore, that's not even the worst part, because on top of drawing way too much geometry, DK Parkway commits the cardinal sin of loading textures multiple times in a display list, and we're going to show that right here. This object I'm going to pick out of the blue. I know that it's going to have a problem because all of the trees have this same issue. We're going to load up the textures for DK Parkway, and notice all of these here. There's 1, 2, 3, 4, 5, 6, 7, 8 different textures for trees. All of them are very similar as well. You can see the textures right here are the ones we're looking at. And going between these, you can see the similarities that many of these share. Slight differences, slight variances in the foliage, most likely variances that no player has ever noticed. I doubt that anybody has sat there and checked out the differences between the plants from one face to another. What they do notice is how poorly the course runs. I promise that they notice that before they notice the differences in those textures. However, those are all going to get used. We're going to go to segment 7, offset FD0, DK Parkway, segment 7, offset FD0 from the beginning. So beginning the display list, setting the RSP segment or sync, loading texture parameters, and here we are. We're going to load the texture at offset 8000. So pulling this up, opening DK Parkway, and the texture at 8000 is this tree. So we've loaded that, synced the RDP again, loaded vertices, and now we can begin drawing triangles. So again, from here to here are all the commands it took to set up the texture and to load the vertices. How many triangles do we draw? 1, 2, 3, 4, 5, 6. After drawing 6 triangles, we load a new texture. This one located here. Instead of this texture, we're using the mirrored half. Differences, not just mirrored, but still the second half of this texture. So load the texture, RDP sync, set the tile parameters, and load vertices. Again, all of these commands to switch textures. How many triangles are we going to draw? 1, 2, 3, 4, 5, 6. Guess what? Load new textures. Set the RDP sync, set the tile parameters, set the RDP sync again, load vertices. How many triangles are we going to draw? 2, 4, 6. Guess what? Load new textures. Are you kidding me? So to recap, we've loaded 8,000, 9,000. Now we're going to load C1000, I'm going to call it. This one. Now we're loading E1000. This one. See this texture here? And this here? And this here? This is why this course runs so slowly. So again, we're going to load these textures, set up all these parameters. How many triangles? 2, 4, 6. Load textures. Set these parameters. How many triangles? 2, 4, 6. And finally, we're done with the display list and we can go back to where we've started. We loaded textures 1, 2, 3, 4 different times in the middle of this display list. Here's the problem. We just did this object right here. I have to do that again for this object, and for this object, and for this object, and this one, 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 and every other time the tree is loaded. Which means that every time I have to draw one of these objects, I have to load textures 4 or 5 times in between. Not for the entire course at once, but for each individual object. So I have to go 1, 2, 3, 4, 5 texture loads, 5 texture loads, 5 texture loads, 5 texture loads, 5 texture loads. And again, that is adding up quick. And the vertex loads in between each one as well, because each time we swap textures and swap faces, we're loading new vertices. I don't know why it has to do that. It's only drawing 6 triangles. It's 18 verts. You should be able to draw more triangles without loading verts again, especially because a lot of those verts are going to be shared between multiple triangles. Again, this is why the course runs so poorly. There are a lot of really bad setups in the FedEx commands. The right way to do that would have been to separate each object by its material, the way that Overcart does it. I would have had 4 or 5 different display objects here, and while that would have been harder to design and set up perhaps, the way that the FedEx calls would have been organized is that it would have called all of the same texture, drawn the object one time, and then switched to a new texture and drawn all those objects again. Again, saving quite a bit for the loading of resources, which is a bottleneck for the system. So I know that a lot of people last time we covered how does Mario Kart 64 video. I had discussed how DK 64 Parkway had struggled, and a lot of people seemed interested in that. This is a really in-depth look on why DK Parkway struggles. There are every display list is too large. They should never be trying to draw this many triangles. I mean, every single one is absolutely massive. Even this corner here is an entire display list from Mario's Raceway. It is incredible, the amount of wasted geometry that seems to be going into rendering this course. And that's the reason that it struggles so much to run it, especially on original hardware. Additionally, that's the reason that many emulators do not run a lot of these courses and a lot of these games properly, is because they aren't accounting for this this variance. Because the emulator is able to run it at 100%, when you play some of these courses, you're actually playing it at 150 or 200% speed. Most emulators, most of the better ones, have no, they have that built into the emulator itself. Additionally, there is a a Game Shark code that will set those tempos to 100%. Something interesting, this Game Shark code was created. The Mario Kart 64 release of Virtual Console on the Wii has these Game Shark codes patched into the ROM. And that is the reason that it runs at a proper speed. They actually took these Game Shark codes, modified the ROM using these same adjustments, and then made that the official download for Virtual Console so that it would run at the proper speed. I think it's pretty funny. I imagine that some dev at Nintendo had this issue, Googled it, found this page, and said, sure, sounds good to me. And that's how we got what we got. So just a funny little story that kind of goes with the topic here. On that note, that is going to pretty much wrap up the video for today. That covers how FedEx works, how it loads vertices, how it loads triangles, and how the display lists are drawn based on those commands. So we went over the display list in Mario Kart, the debug mode, and how to view the different display lists that should be drawn, what triangles are drawn in those display lists, and then, again, how the FedEx commands actually work. If you'd like to be kept up to date on continuing Mario Kart 64 modding news, please click the link at the end of the video to subscribe to the Overkart 64 YouTube channel. Additionally, if you're watching this currently on the Dead Hamster YouTube channel, there is now an official YouTube channel for Overkart 64, and it is where we will be posting the majority of content going forward for Mario Kart 64 modding. So if you want to stay updated with all of Mario Kart 64 modding news and updates, please again subscribe to the channel using the link at the end of the video. If you have any questions or any comments you'd like to make, please post them in a comment down below, and I'll be happy to answer as best I can. And again, thank you so much for sticking through and watching this video, and I hope that it was informative. So thank you again, and enjoy the rest of your day. Take care.